Welcome back to The Explainer. Today, we're diving into something that honestly feels like it's straight out of a sci-fi novel, but is actually a very concrete target for the world's top research labs. We're mapping out life past the edge of our current technological understanding. We're talking about that uncharted territory between AGI and ASI.
Which really just brings us to the ultimate question, doesn't it? Is the singularity actually near? I mean, for decades, we've debated when machines might finally reach human-level intelligence. But what happens the day after that? What happens when growth just totally accelerates, and human-level AI is no longer the final endpoint, but literally just a stepping stone?
Okay, let's dive into this. To help us actually chart this map, we're unpacking a really fascinating 2026 research report out of Google DeepMind, authored by Tim Genowine and his colleagues. This paper gives us a highly rigorous framework to understand how AI might evolve once it finally matches our own cognitive abilities.
So here is our roadmap for today. We're going to cover 1. Life beyond AGI. 2. Defining artificial superintelligence. 3. The digital advantage. 4. 4 pathways to ASI. 5. Roadblocks and bottlenecks. And finally, 6. Navigating the unknown future.
All right, let's jump straight in. Section 1. Life beyond AGI, extrapolating the current trajectory. We really need to start by correcting a super common assumption. A lot of people tend to view human-level artificial general intelligence as this final finish line. But biologically speaking, human intelligence is just one very specific point on a massive continuum. There is absolutely no fundamental law of physics that says intelligence has to stop at the median human brain. To put why progress feels so incredibly explosive right now into perspective, just look at this number, 10x. According to the research, the amount of effective compute being pumped into frontier models is estimated to be growing by about a factor of 10 every single year. And this isn't just about microchips getting smaller, right? It's this massive compound effect of better hardware manufacturing, huge global investments, and crucially, incredible improvements in algorithmic efficiency. Think about it like this. Imagine if your car got 10 times faster and 10 times cheaper to fuel every single year. That is the compounding reality of AI today.
Moving on to Section 2, Defining Artificial Superintelligence. What lies at the destination? To safely navigate all this uncharted territory, we really need to make sure we're on the same page with our terminology.
Now, what's really interesting about what we're looking at here is the sheer scale of the difference. AGI is basically used as a shorthand for a single brain, essentially an AI that's as smart as your median human. But ASI is a massive structural leap forward. It doesn't just mean a really smart individual AI. It refers to a system that completely blows past the capabilities of entire large organizations of human experts across virtually all tasks. We're literally talking about outperforming thousands of coordinated top-tier specialists working together over a decade.
Okay, Section 3, the digital advantage. Why machines scale differently. So, why is ASI seen as virtually inevitable if our current progress continues? Well, it fundamentally comes down to the fact that digital intelligence just possesses built-in structural advantages over biological intelligence.
Let's look at how this builds a really strong case for rapid scaling. Humans are amazing, obviously, but we have strict limits. Our input and output speeds are painfully slow. We have to type, we read, we speak, and we actually have to stop to sleep and eat. Digital AI, on the other hand, has high bandwidth ingestion. It can read the entire internet in a fraction of a second. We're tied to these fragile physical bodies, whereas AI has substrate independence, meaning it can be migrated to newer, faster hardware instantly. And while human teaching is incredibly lossy, meaning knowledge gets forgotten or misunderstood from generation to generation, digital intelligence features lossless replication. An AI can simply copy its exact entire memory state to millions of other instances in the blink of an eye.
But we definitely need a reality check here. ASI is not going to be some magic genie. It's not perfectly omnipotent or omniscient. It is absolutely still bound by the fundamental laws of physics. Information literally cannot travel faster than the speed of light. Erasing data still costs physical energy. That's the Landauer principle. Plus, any physical manipulation in the real world, like building new factories or testing out new chemicals, is heavily constrained by real-time latency. Things just take time to build. And of course, deep mathematical limits, like P versus NP in complexity theory, still firmly apply. Even a superintelligence can't just instantly guess the perfect solution to exponentially complex problems.
Which brings us to Section 4, 4 pathways to ASI, the roads ahead. Knowing what ASI actually is, How do researchers predict we'll finally get there? Well, they've mapped out 4 distinct but parallel technological roads. Let's walk through these sequentially just to manage our cognitive load a bit. Number 1, scaling compute, models, and data. Number 2, algorithmic paradigm shifts. Number 3, recursive self-improvement. And number 4, multi-agent coordination. Now, while these are all happening totally in parallel at the world's top labs right now, each one represents a completely distinct mechanism for evolving intelligence.
So the crucial point is really the contrast between those first 2 pathways. Brute force scaling, literally just throwing way more data and larger compute clusters at our current transformer models, might actually be enough to push us into ASI simply by running millions of AGI instances all at once. But scaling often hits massive diminishing returns, and that's exactly where paradigm shifts come in. This pathway assumes we're going to need completely novel architectural leaps to keep progressing. Things like linear time sequence models or totally new ways of processing memory that break away entirely from today's standard neural networks.
Now, that third pathway, recursive improvement, this is truly fascinating because we can map it almost directly to human evolution. Think about it. Genetic evolution for an AI basically means it autonomously modifies its own source code and optimizes its own architecture. Cultural evolution is the AI completely automating its own dataset creation, perfectly curating the absolute best synthetic knowledge to train the next generation. And cooperative evolution completely mirrors human societies. AIs dividing up labor, creating hyper-specialized agent subgroups that trade information flawlessly. The whole shebang creates this autonomous bootstrapping loop where the AI is literally driving its own research and development.
All right, Section 5, roadblocks and bottlenecks, the speed bumps. Let's pivot to the reality checks. What are the major friction points that could prevent, or at least drastically slow down, an intelligence explosion? The first massive speed bump we're going to hit is known as the data wall. We are rapidly, and I mean rapidly, exhausting the global supply of high-quality, human-generated text on the internet to train these models. But frontier labs definitely aren't just throwing in the towel. They are aggressively developing workarounds or counterfactors. They're generating vast amounts of high-quality synthetic data, spinning up high-fidelity physical simulations, and leaning heavily on reinforcement learning, where the AI essentially learns by playing against itself in an infinite loop, exactly like AlphaZero did with chess. Then there is this brilliantly profound bottleneck called the abstraction barrier. It's this working hypothesis that an AI, if trained solely on human text and concepts, might never actually discover fundamentally new physical primitives entirely on its own. Imagine an AI trying to truly understand the concept of gravity without ever existing in the physical world to drop an apple and physically feel its weight. That complete lack of grounded real-world interaction might act as a very natural speed limit, literally stopping an AGI from generating true paradigm-shifting physics simply by reading more text. We also face some extreme physical and economic friction. Look, building ASI requires staggering physical resources. We're talking gigawatt power grids, massive data center land use, and insanely complex supply chains for rare earth metals. The huge tension here is whether the incredible economic returns generated by early AGI, automating tasks, rapidly accelerating science, will actually be enough to financially support and justify building the unimaginably massive infrastructure required to push all the way through to ASI.
All right, final stretch. Section 6, navigating the unknown future. What happens next? We've successfully mapped the pathways and the roadblocks, but what are the actual, real-world societal implications of crossing this border?
Because look, the arrival of ASI likely won't be some single sudden flash in the pan. It's going to be a series of highly complex, messy societal transformations. We absolutely have to worry about instrumental convergence, which is the idea that any highly autonomous AI might accidentally formulate unintended, dangerous goals, like hoarding resources, simply to accomplish its basic tasks. We also have to account for massive societal backlash and the very real possibility of governments deliberately enforcing strict regulatory slowdowns. Furthermore, we desperately need completely novel benchmarks just to even test if a system is superintelligent, because all our current tests max out a human expertise. And hovering ominously over all of this is what researchers call military economic adaptationism. This is the intense geopolitical race where nations just feel totally forced to adopt these technologies simply to survive globally, basically regardless of the domestic risks.
And this brilliantly illustrates our exact position today. Alan Turing nailed it way back in 1950 when he wrote, "We can only see a short distance ahead, but we can see plenty there that needs to be done."
Even in the face of exponential computing growth and massive uncertainty about the actual timeline, the tasks sitting right in front of us, aligning AI, managing our data resources, and figuring out multi-agent governance, are crystal clear.
Which leaves us with this final, incredibly profound thought to ponder. We spend all of our time wondering if and when we will finally build human-level AI. But the map we looked at today shows that human level is just a transit stop. So I have to ask you, what happens after we build it? And honestly, more importantly, as the map extends way out into the realm of superintelligence, what exactly is humanity's role in a post-AGI world? Thank you so much for joining me to explore this incredible research. Keep learning, keep questioning, and I'll see you in the next explainer.